Unit 1A, Lesson 3. The one standard we are going to discuss in this lesson: extend polynomial identities to the complex numbers. For example, we're going to rewrite x squared plus 4 as x plus 2i times a quantity x minus 2i. Before we get into solving problems, we need to make sure you understand what a polynomial identity is. A polynomial identity is simply two polynomial expressions that are equal to each other. Okay, so there's many different polynomial identities we can have. One of the most common ones is a difference of two squares. We have a squared minus b squared. This is a polynomial. We have a plus b times the quantity a minus b. Technically, that's a polynomial too. They're equal to each other. This is an identity. Before we get into working with polynomial identities, we're going to review a problem from the previous lesson. Write a polynomial of least degree with real coefficients and the given roots. The only root that we're provided with is 13 plus 8i. Using the complex conjugate theorem, we know if we have a complex root, there must be a conjugate pair to go with it. So this means that 13 minus 8i must also be a root to this polynomial. Now, writing this in factored form, we have x minus 13 plus 8i, and then we have x minus 13 minus 8i. Rearranging these terms a little bit, this is going to be equal to x minus 13 minus 8i, and then we have x minus 13 plus 8i. If you recall from the last lesson, we can use the FOIL pattern to FOIL this out because we're thinking of this as one term. This will be equal to x minus 13 quantity squared. Multiplying the outsides, we have plus 8i times x minus 13 minus 8i times x minus 13. And then we have 8i times 8i, which would be minus 64i squared. These middle terms, we have a positive and a negative. Those are going to cancel each other out. So if we look down below, we can simplify this a little bit. This is the same as x minus 13 times x minus 13. 64 I squared, and recall I squared is equal to negative 1, so you have negative 64 times negative 1, which is plus 64. Using the FOIL pattern again on x minus 13 times x minus 13, we would get x squared minus 26x plus 169 plus 64 at the end. Last thing is we need to combine like terms. So we have x squared minus 26x, 169 plus 64, 170 plus 60 would be 230. So this is going to be 233. This is a polynomial of least degree that has these two complex roots, right? Remember, these are a complex conjugate pair. They have the same a and b value. The only difference is the sign in between them. Final example, use common polynomial identities to rewrite each expression. But first, suppose we have x squared minus 25. You should recognize this pattern. This is a difference of squares, which you know will factor into x plus 5 times x minus 5. What if I change the sign in the middle though? Now we have x squared plus 25. Okay. A little more difficult, if we would set this equal to 0 and try to solve this, we would subtract 25 to the other side, which would leave us with x squared is equal to negative 25. Right now you should have a red flag going. We know if we square any number, we're going to get a positive answer, but this is equal to a negative value. That means our solutions to x squared plus 25 are going to be imaginary numbers. All right, so taking a step back, if we have this same form and the only difference is that we have a sum, so we have a sum of squares, we're still going to follow the same general pattern that we do for a difference of squares, except now this is going to factor into x plus 5i times x minus 5i. Notice we're going to have two imaginary solutions. We're going to go through the process of foiling this out to show you that this gets us back to where we started. If we FOIL this, x times x is x squared. If we take our outside, x times negative 5i, so negative 5ix plus 5ix, and then 5i times 5i, we're subtracting 25i squared. Middle terms cancel out. We're left with x squared. I squared is equal to negative 1, so negative 25 times negative 1, x squared plus 25. Back to where we started. So if you can recognize this is close to our difference of squares, except now it's a sum of squares, we know we can factor it with a similar pattern. It's just going to have imaginary solutions instead. Now we're going to solve a problem that is a little more difficult. All right, we have x cubed minus 1. You might recognize one of the solutions to this is going to be a value of 1. If we would set this equal to 0, add 1 to the other side, x cubed equals 1. We know if we plug 1 in for x, 1 to any power is going to be equal to 1. So knowing that 1 is going to be one of our solutions, we can rewrite this as x minus 1, and then now we're going to have some quadratic left, but we don't know what that quadratic is that this factors into. Okay? We can use synthetic division to find that. You might not remember synthetic division. I'm going to go through that quickly to find out what the other quadratic, or the quadratic that remains, is going to be. To use synthetic division, we create our little box. The coefficient in front of x cubed is 1. There's no x squared term, so we fill that place value with a 0. There's no x term, so we fill that place value with a 0, and we're left with negative 1 at the end. We said 1 is one of the solutions to this problem, so that's the value we put on the outside. First, we bring this first number down, that 1, multiply across. 1 times 1 is 1. Add vertically, 0 plus 1 is 1. 1 times 1 is 1. Add vertically, 1. 1 times 1 is 1. Add vertically, we have a remainder of 0, which is a good sign. That means x minus 1 goes into x cubed minus 1. Now we started with x cubed. This is going to be a degree 1 less than. So this is going to be x squared plus x plus 1. That is a quadratic we're left with. X squared plus x plus 1. Now we want to take that quadratic, x squared plus x plus 1, and we want to find the solutions to that. Easiest thing to use in this case is probably going to be the quadratic formula. Our a value is 1, the b value is 1, and the c value is 1. Alright? X is equal to the opposite of b, so negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 1. all divided by 2 times 1. Simplifying this out, we have -1 plus or minus 1 squared is 1 minus 4. So this is the square root of -3, all divided by 2, which we can break this up into -1/2 plus or minus the square root of -3 over 2. We want to rewrite this as a complex number with I. This is going to be equal to -1/2 plus or minus radical 3 over 2 with that I in front of that. These are going to be, we have two solutions here, the positive and then the negative. We started with an x cubed, so we should have 3 solutions. We said 1 is one of the solutions, and then we can see we have both of our solutions down here. Now that we know all 3 solutions, we can break this down into the 3 individual factors. Final factorization is x minus 1 times x minus the quantity -1/2 plus I radical 3 divided by 2 times the quantity x minus -1/2 minus I radical 3 divided by 2. We had to use polynomial identities and the quadratic formula to rewrite this in an equivalent form. Next example, we have x to the 4th minus 1. Again, we want to use polynomial identities to rewrite this in an equivalent form, break it down. We can treat this as a difference of squares. So this factors into x squared minus 1 times x squared plus 1. X squared minus 1, that's the difference of squares. That will factor into x plus 1 times x minus 1. X squared plus 1, this is a sum of 2 squares. Okay, so we're going to treat it very similar to the one we just did with the difference of squares, except now we're going to have imaginary values. So x squared plus 1, we can rewrite that as x plus 1i, which is just going to be x plus I, times x minus 1i, which is just x minus I. This one was actually quite a bit easier. If you can recognize that x to the 4th minus 1, we can apply the difference of squares property. Again, apply the difference of squares property to break down x squared minus 1. And then we have a sum of squares, which we treat very similar. We just have those 2 imaginary solutions. In this lesson, you reviewed how to write a polynomial of least degree when given a root. If you have a complex root, you know it occurs in conjugate pairs. You also reviewed the quadratic formula and synthetic division. The main goal behind this lesson, though, was to use polynomial identities on the complex numbers. You probably realized or recognized that we're going to use the difference of squares pattern quite often. Okay? So being able to apply all of those things we learned back in Algebra 1 to complex numbers now.